We'll now actually define the matrix inverse and how to find it. And we'll start with this simple case, the 2 by 2. If we have a 2 by 2 matrix A that's given by A, B, C, D, then the inverse is 1 over AD minus BC times the matrix D minus B minus CA, provided that AD minus BC is not equal to 0. If it is equal to 0, then we have a singular matrix. The idea is we're going to cross multiply A times D and B times C and then subtract. We flip the values on the main diagonal and change the signs in the other two spots. Let's look at this example. The first thing we do is A times D, 3 times negative 2, minus B times C, negative 1 times 7. This gives us negative 6 plus 7, which is 1. Therefore, our inverse is 1 over 1. We then flip the elements on the main diagonal and change the signs in the other two places. Therefore, the inverse of this matrix is negative 2, 1, negative 7, 3. Our 3 by 3 case is a little more complicated, and this is 3 by 3 or higher. We're going to start by forming an augmented matrix where A is on the left and the identity matrix is on the right. Then we'll reduce this using our row operations. And when we do, we'll try to get the identity on the left, and then our inverse will pop up on the right. Here I have a 3 by 3 matrix that I'm going to try to take the inverse of. I'm going to erase this side to form my augment and put the identity matrix on the right. And then we need to use row operations. I already have a 1 in the first row, first column, so we'll try to get zeros below it. For the first one, I need to add 2, so I'll do 2 row 1 plus row 2. That would be 2 minus 2 is 0. 8 minus 6 is 2. 20 minus 12 is 8. 2 plus 0 is 2. 0 plus 1 and 0 plus 0. For my third row, I will just add my first and third row. 1 minus 1 is 0. 4 minus 2 is 2. 10 minus 4 is 6. 1 plus 0 is 0. 0 plus 0, and then 0 plus 1. Once we've done that, we need to get a 1 in the second row, second column. And this time, our first and third rows will stay exactly the way they were before this row operation. And in order to do this, I'll divide this row by 1/2. 1/2 times 2 is 1. 1/2 times 4, or 1/2 times 8 is 4. 1/2 times 2 is 1, and then I have 1/2 times 1. Now that I've done that, my goal is to get zeros both above and below this 1. When I do that, my first and second rows, or my second row will stay the same. The first and the third will change. For the first one, there's currently a 4 there, so I need to multiply by negative 4. Negative 4 plus 4 is 0. That would be negative 16 plus 10 is negative 6. Negative 4 plus 1 is negative 3. Negative 4 times 1/2 is 2, or negative 2. And then we have 0. To get the 0 below, I need to multiply by negative 2. Negative 2 plus 2 is 0. Negative 8 plus 6 is negative 2. Negative 2 plus 1 is negative 1. And then we have negative 1 plus 0 and 0 plus 1. My next step is to get a 1 in the third row, third column. So my first and second rows will not change here. I would need to multiply by -1/2 to get 1. That would give me a 1/2, a 1/2, and a -1/2. Finally, I'll get zeros in the rest of the third column. My last row is set. To get the 0 in the first row, I would need to multiply by 6. 6 times 1/2 is 3, minus 3 is 0. 6 times 1/2 is 3, minus 2 is 1, and 6 times -1/2 is -3, plus 0. To get the last 0, I would need to subtract 4, so we'll do -4 plus 4. -4 times 1/2 is -2, plus 1 is -1. -4 times 1/2 is -2, plus 1/2 is -3/2. And then -4 times -1/2 is +2, plus 0. Therefore, this last entry here is my inverse. We'll now do a second example. Here, I already have a 1 in the first row, first column. So we'll move to the getting zeros in the second row and the third row. The first one's a 2, so I need to do -2 row 1 plus row 2. That would be -2 plus 2 is 0. -6 plus 4 is -2. -14 plus 8 is -6. I would then have a -2, a 1, and a 0. To get the third one, I can just subtract row 1 plus row 3. That would be -1 plus 1 is 0. -3 plus 1 is -2. -7 plus 1 is -6. And then I have -1, 0, and 1. And the fact that these last two rows look exactly the same here should cause you concern. I'm going to go ahead and subtract row 2 minus row 3. When I do that, I get zeros here and here. Therefore, this does not reduce to the identity matrix. So this is a singular matrix. The inverse does not exist. We'll now talk about matrix equations. And here I have the general form of a system of equations. Well, we can actually write this as the matrix A times the vector x is equal to the vector b. This matrix A is just my coefficient matrix. This matrix X, these are a list of my variables. And then the B are the constants. So this is going to be another way for us to represent a system of equations that we will use quite often now. And we'll look at one theorem about these matrix equations. If we have A is an invertible matrix, then the system of equations Ax equal to b has a unique solution no matter what vector b is. In particular, the solution is given by A inverse b. We'll now look at proving this. Well, we have this system of equations Ax equal to b, and we know A is invertible. So all we have to do is multiply both sides by A inverse. Once we do that, on the left we'll get an x, and on the right we get the A inverse b. Therefore, as long as you're invertible, you have a unique solution.